Hi, we're Team 14. My name is Matt Bollinger.
Brendan Smith.
Sapar Sorabi.
And this is our rover.
So the objective of our project was to create an autonomous rover using our ARM processor, which would basically act as the brains of our operation and make decisions for the rover. We were also provided 8-bit microcontrollers, which from now on in the video we refer to as PIC boards. And then we also use data from our sensors and motors that are on the rover. We use this data to discover where our rover is on a map that has been given to us, and then from there we try to use that data to navigate to a target location on the map.
So I'm going to talk about the master PIC, which is our communication hub for the rover. It communicates with the sensor PIC and motor PIC via I2C, and it kind of just communicates back and forth, sending and receiving data. It sends all of that to the ARM board over a Wi-Fi and a dedicated ARM PIC that is also connected by Wi-Fi. The master PIC also implements what we call a local control that, depending on what sensor PIC data we get and what the ARM tells it to do, it will, while the rover travels forward, it will maintain parallel with the wall. So if we are moving forward and starts to deploy to the left, it'll turn the rover back around to go back to the right to straighten itself out. And in addition, it will also use those kinds of parallel algorithms to ensure parallelism and stop, if necessary, when a wall is in front of it.
So we have 6 total infrared sensors on our rover. We have 1 for front and back each, and then 2 on each side. The point of having 2 on the sides is to detect whether or not our rover is parallel or not. So when we're moving parallel, normally we would see that both this sensor and this sensor are emitting relatively equal distance. If for some reason we're moving along the wall at an angle, we will see that this sensor is creating a significantly higher distance value than this one, which will be able to tell the rover that it needs to correct itself, and then it will continue moving forward. So I'm just going to give a brief overview about how the sensor PIC works. Basically, the way everything gets started is from the timer. A sensor receives a reading every 50 milliseconds. And so we have a timer set to go off every 50 milliseconds. From there, it'll enter an interrupt, which will go ahead and take all the sensor data and send it into this main function here. The main function does is basically takes the sensor data, and then the sensor data is raw digital data at this point. So what we want to do is convert it into more meaningful units. In our case, we convert it into inches. From there, it will sit there and wait until a request is received from the master PIC saying it wants sensor data, and then from there it will just send it via I2C. So one of the biggest problems that we had with the IR sensors was they were very susceptible to light. If the lighting changed for whatever reason, or if it came across a more reflective surface, then it would cause the readings to be inaccurate. Another problem that we had was noise in general, especially since we had our saber-tooth motor encoders and all our sensors on one circuit. It really created a lot of noise within the sensors, which would also lead to more inaccurate readings.
Our rover has 4 motors, 2 on each side, and the motors on each side will move at the same speed and in the same direction. So we can have the rover turn by having the motors on one side move at a different speed or in a different direction than the ones on the other side. The motor PIC, which is an 8-bit microcontroller, works by receiving commands such as go straight, turn right, or left, or stop from the master PIC, and then sending a serial UART signal to the saber-tooth motor controller, which is directly connected to the 4 motors and will send them an exact speed and direction so that they can move. There are also two encoders, one on each side of the rover. The encoders display the number of ticks that the motors generate as they turn, and the output of the encoders is sent to timers on the motor pick as an external clock source. This provides us the distance that the rover has moved, accurate up to 1 inch. We only count the distance if we're going forward, and we ignore the encoder distance data when the rover is turning.
The first part of our algorithm is wall generation. So we're given a set of vertices that correspond to the corners of the cell hallway. Using the vertices, we generate walls that correspond to the hallways, or the walls of the cell hallway. So using the vertices, we will generate a wall that has the start and end vertex, as well as how long that wall is. So once we generate all the walls, they'll also know which ones they're connected to. So this wall being connected to this wall, that one, all the way around the map, so that once we start trying to figure out where to go, we can just follow the path of the walls to our destination. The second part of our algorithm is exploration, or finding out where we are. We know what the map looks like, but we don't know where we are in this map. So assuming we start in a corner, we will travel along a wall for the entire length of that wall until we get to the next corner. Once we have reached this next corner, we'll read from the encoders how far we've gone, and we'll try to match that distance traveled to a length of the wall. So say we're traveling along this wall right here that's 79 units long. When we get to this corner, we'll read the data and we'll try to match that distance traveled, which is around 79, to this wall. And this will work for any of these walls. So we start here and go here, we'll be back 12. But the inherent downside of this algorithm is that it only works for maps that are have unique wall lengths. So if we had a box, this wouldn't work because each of the walls would be the same and we'd be looking forever. But because the cell has unique wall lengths, this algorithm will work and work within usually at least one wall, maybe two. So now that we know where we are in the map, we will try to get from wherever we are to our target destination. So what's going to happen is we figure out where you are, you're going to be in a corner. So say we're in this corner, we're trying to get to this target over here. We'll look at all of our list of walls because they know you know where you are and you know how all the walls are connected. We'll try to make a path going from this corner to this target by just following the walls. And then we'll get to this corner, and from there, because we're not at the mathematical point of this corner, we're going to be outside because the rover isn't on the wall. We'll be at the target within around 6 inches of that target.